Hello all, my name is Kai Pressler-Marshall and today I'll be presenting my work, SQLRepair, Identifying and Repairing Mistakes in Student-Authored SQL Queries, a project I've worked on with my advisors, Dr. Sarah Heckman and Katie Stoley at NC State University. So, first off, why do we care about any of this? Well, imagine you've got a table of data that you're working with stored in a relational database that looks something like this, and you want to go transform it into another smaller table of data. If you've worked with relational databases at all before, you're probably thinking, let's go write a SQL query. But perhaps instead of being an expert, you're a relatively novice student who's working with SQL for the first time. So you write a query that looks something like this. And you take your query and you go execute it using a MySQL database or similar, expecting to get back a table of results. But instead you're greeted with an error message. And in particular on MySQL, you get error code 1054, unknown column US in where clause. And you're not sure what this means, so you go and Google the error message and you go click on the first Stack Overflow post that you find, which in our case was this one right here, which says you have to use proper single quotes instead of weird quotes around your strings. Well, we don't have any weird quotes on our strings, but we also don't have any quotes at all, so maybe they're on to something here. So you make this fix, and then you have a query that looks something like this, and you go execute it again. And this time it at least executes successfully, and you're greeted with a table of results. But it's still not right. There's too many columns here. So you search for that error message as well, and you find another Stack Overflow post that says, go replace the wildcard star with the column names that you want to get back. So you make that fix your query as well, and so on and so forth, fixing one mistake at a time. But over time, this eventually becomes less educational and more frustrating. So wouldn't it be nice to have a tool that would help you with this process? Well, we think that it would be, but first we need to understand the types of mistakes that students make so that we can tune the tool appropriately. In this work, we classify the types of errors that beginning students make when writing SQL queries. We also present SQLRepair, a tool that is capable of some automated repairs to SQL queries, and we demonstrate that the repaired queries are as useful as human-written ones. So, to guide and structure our work here, we proceed with 3 research questions. First, RQ1. What types of mistakes do beginners make working with SQL? Second, RQ2. How well can SQLRepair fix errors that are introduced by beginning programmers? And finally, RQ3. How understandable do students find repairs made by SQLRepair? So, in order to answer each of these questions, we designed a study that would help us answer each of them in turn. So, we recruited students from 2 undergraduate computer science courses at our university, a second-year Java Programming CS2 course, and a third-year software engineering course. Our student participants were invited to sign up for virtual lab sessions where they were given a brief introduction to SQL and then tasked with solving problems with it. For each problem, students were given a source-destination table pair, like we have over here on the left side, that illustrated a transformation that we wanted them to perform. And then they were tasked with writing a SQL query that would be capable of performing the transformation. Then the students took the queries that they wrote and submitted them into a web application that we wrote, which would execute each one and check it for correctness by comparing the expected results against the results that were actually returned by the database. If they were the same, the student was congratulated. Otherwise, they got feedback on what went wrong, either in the form of the error message from the database or the actual table of results that was generated. Next, after either solving the problem successfully or attempting it multiple times and ultimately giving up, we asked students to vote on alternative queries, presenting them with several queries, including repairs produced by our tool, and asking them to rate the understandability of each one using a modified 7-point Likert scale, optionally explaining the rationale behind their vote as well. So that's what the student participants in our study did, but what did we do with the data we collected from them? Well, we took the queries that our student programmers wrote, and we executed each one against a MySQL database to check it for correctness. If the query was correct, we put it to the side because our primary focus here is on the incorrect queries. So, first, for RQ1, we analyzed these incorrect queries that students wrote looking side by side at the incorrect query itself and the output from the database, either an error message or an incorrect table of results, which let us identify the mistake or mistakes that were present in the query. Next, we took these incorrect queries and submitted them to SQLRepair, our automated repair tool, to attempt automated repairs upon them. For queries that it could not fix, we spot checked a couple to see what was wrong, but predominantly focused our efforts on the fixed queries where it was able to produce a repair. This was what we did for RQ2, looking simultaneously at the fixed query that was produced as well as the incorrect query that was provided to SQLRepair to see what was changed in it and thus classify the types of repair operations that were performed. Finally, for RQ3, we performed statistical analysis on the student votes on which queries they found most understandable. Because students were shown multiple queries side by side, we performed a series of paired Mann-Whitney-U tests to see which query categories they found most understandable. We followed this up with some brief qualitative analysis on their explanations as well, seeing beyond what the numbers would tell us about why they preferred certain queries over others. So that's what we did, and what did we see when we did so? Well, first for RQ1, the types of mistakes that beginners make. We observed that only 9% of queries that students in our study wrote are correct, falling further to 8% among our most junior CS2 students. We observed that students made both syntax errors and semantic errors in many queries that prevented them from executing correctly. So first we have an example of a query with a syntax error, where a student wrote a query that includes both a wildcard star and a column list. Next, a query with a semantic error. And the mistake with this one is it's a little bit harder to see, but the student wrote a query that contains the wrong constant here, thus resulting in the wrong set of rows being returned to the user. Next, for RQ2, the quality of our automated repairs. We find that SQLRepair can fix about 29% of the incorrect queries that students wrote, covering both syntax and semantic errors. And additionally, we see that about 82% of the repaired queries, the vast majority of them, require multiple distinct repair operations to be performed in order to correct the query. And we have an example of what that looks like here, with an incorrect query from a student up top and a fixed version from SQLRepair at the bottom. So first, our tool identifies the column list present is incorrect and replaces it with the one from the destination table. Next, it identifies unquoted string literals and adds quotes to them so the database won't treat them as additional columns. And finally, it identifies the original where clause is not sufficiently restrictive and returns the wrong set of rows to the user. And it removes an extra subclause that inhibits correctness. Finally, for RQ3, the quality of the automated repairs performed by our tool. We observe that there is no statistically significant differences between any query types that were present, thus suggesting that students find all of the queries to be equally acceptable solutions for solving a problem. However, some students even preferred a repaired query from our tool to their own solution for a problem, thus suggesting that automated repair may be helpful for giving students another option to visualize when peer discussion and comparison is unavailable. So we've covered a lot of ground here and we found out a bunch of new things. But what is it to take away from all of this? Well, first, we observe that the vast majority of queries that students write are incorrect, mostly due to semantic errors, yet syntax errors remain prevalent and persistent as well. Additionally, our results suggest that automated repair may be useful within SQL education or perhaps more broadly within computer science education. Our tool is able to fix a non-negligible number of queries that students write that had mistakes, and students find the repairs produced by our tool to be understandable, as good as queries written by themselves or by other students, and in some cases, even better. That's all that we've got for today, but if you have any questions, I would be delighted to take them in the session next. Thank you.
Hey, hello, we are here in the QA part of our third paper in this session. Katie and Kay are here with us to answer all the questions and discuss all the issues that the audience may have. So please introduce your questions and comments in the chat. As we don't have any new comments yet, so I will start with a question that I have. In your study, you mentioned that most of the solutions that you found are incorrect solutions, and you only detect around 9% of correct solutions. Isn't it? Okay.
Yep.
So, do you think that it would be possible to give the students in advance some guideline or some information to prevent those errors from the knowledge that you have gathered from this experience? That is, use this knowledge for future editions, and instead of counting the mistakes, trying to prevent such mistakes?
Yeah, absolutely. Thank you for the question, Dr. Moreno. So we think that the results of what we've seen in this study can be used both in a reactive and in a proactive fashion. So we've demonstrated our tool is capable of fixing some of the mistakes after the fact. But better yet, because we have seen the types of mistakes students make, we can help ward off the mistakes going forward. So we've seen that students particularly struggle with certain types of problems. For instance, students have a very hard time with problems that involve joining together multiple different tables. We saw that we hypothesized that they struggled with visualizing the relationships across those different tables of data. So we think we can use the types of mistakes we've seen in the past to tailor lessons around that, to give students pointers on here, these are things to think about, encourage them to go look for relationships between the data, maybe discuss that with someone else that they are working with, someone else who's working through the activity, sort of a pair programming with SQL queries, where we give them these are things to look out for and maybe a partner to discuss with as well.
Good. Okay. And then I have another question. Why do you think, because you mentioned that the students used to like more the solution given by the tool than their own solution. So why do you think that is this, which is the reason? Do you have information gathered from the students, or any feedback, or any insights or intuitive idea about what is the reason?
Sure, thank you. So what we found is that there was no statistically significant differences between student preferences for any of the query types. There was a slight non-significant preference for their own solutions, but in some cases they actually found our tool produced solutions to be better than their own. And we asked students to elaborate if they wanted to on why they preferred a certain solution. And we saw that for some students, there was basically an aha moment of, yes, I managed to solve this problem, but it wasn't an optimal solution. It wasn't how they would have solved it. Maybe if they'd taken a bit more time on it, if they'd come back to do it again. So I think as software engineers, we all have this experience of, we take a look at something that we've written later on, and you're like, I can't believe how stupid this was, or I can't imagine I didn't think of a better way to solve the problem. And we think that this happened with some of the students as well. They solved the problem, they came up with a solution that worked, but then upon viewing another one, some of the repairs from our tool were cleaner and more concise than their solutions were. So they saw the repair and was like, oh yeah, I could have done it like this. Why didn't I think of doing something like that? So we think this is why in some cases they had a preference for ours. And we received comments to that effect as well. One student literally said, I can't believe how a word similar to bad my answer is. So we think that they liked our solutions in those cases.
Okay, good. So from the audience, is there any question or comment? Please write down in the chat, they are very welcome. Okay. In the meanwhile, which do you think that is the most difficult or the most challenging task for you in this experience as teachers, as professors or instructors?
The most difficult task when it comes to helping students, it's probably that different students come in with different backgrounds, different
Okay.
different experience they have already. So this summer I'm teaching a CS 1.5 course. I have some students who many of my students are computer science majors. Some of them are doing a computer programming certificate. Some of them are taking the class to fulfill other requirements. And maybe some of the would-be computer science majors, they've been programming on their own for a couple of years at this point. They get to the class and they're like, well, all of this is obvious. Can you go faster? Can you talk about interesting stuff? But I can't do that because I have students who have um, they're equally interested in the material. They have an equal drive to succeed, an equal desire to learn the material, but maybe they didn't happen to have the opportunities at home, the support from their high school, to take more of the programming classes. And I think the same applies to the SQL activities as well. We see in a more upper level software engineering course where we cover databases explicitly. Katie is actually the coordinator for said course. Some of the students come into this class having worked with databases in their internship. So when we run them through an activity on learning how databases work, learning how SQL works, solving some problems with it, some of the students blow through the activity in 15 or 20 minutes, and then they're like, well, what do we do next? What do I do now? I'm bored. Um, but it takes some of the other students longer to pick up the material, which of course is fine if you're covering something the first time. It will definitely take longer.
Okay, thank you. We have a question by Max. He says, maybe I miss it. Could your tool generate textual explanations for the change needed to repair a query? This type of additional feedback, in addition to the correct answer, could be quite valuable.
All right, thank you very much for the question, Max. So the short answer is it doesn't generate an explanation for why an answer is or why a change is necessary. So it will show you a diff of this is the query you started off with, this is the repaired version of the query, and then here's a string diff of the changes that were made. So you can see that a constant was removed and a new constant was put in its place, or we removed a subclause from the query. Um, but sort of like machine learning algorithms, it doesn't tell you the why things happened, just here's what it did do. So that would be a fascinating direction for future work to see, can we generate not only this is what needs to be done, but this is why it needs to be done, and this is why you might want this change in particular, as opposed to something else that might solve the problem, but we can't come up with an articulate explanation for it.
But if I may, so I think Max has actually identified an opportunity here, because with the SQL repair, unlike more general program repair work, the scope of our changes is relatively small, because we're changing the columns, we're changing an operator. And so with that small scope, we might actually be able to generate explanations in a more intuitive way because we have less space to cover.
And perhaps in particular related to that, you could say the tool could generate an output message saying, hey, we changed constant from A to B because it results in the inclusion of these rows or the exclusion of those other rows. So I think it is very feasible for it to show this is basically what you get as a result of each of the changes that are made. This column gets dropped from the output, this row gets included into the output, that sort of thing. So yeah, that's a great direction for future work, and not something actually we'd considered beforehand, but thank you, Max.
Okay, cool. So we are almost out of time. So thank you, Katie and Kai, for the presentation, for the discussion, and thank you to the audience also, and to the authors that posted their questions. Okay, so have a nice evening. We will go to the next paper. Bye-bye.
Thanks.
Bye.
Thank you.